We are diving deep into a monumental piece of work today. The massive survey paper, Memory in the Age of AI Agents. A survey.
And it really is massive. But it's also, I think, incredibly necessary. If you've been following agent research, you know that the term agent memory has gotten, well, fragmented.
Right. It means 15 different things depending on which paper you're reading.
Exactly. And this paper tries to fix that. It cuts through the noise with a single, really coherent framework built on 3 pillars: forms, functions, and dynamics.
Okay, so this is the hook, the new architecture we all need to get our heads around. So let's break it down. Forms. That's about how the information is stored, right? Is it text? Is it in the model's weights or somewhere else?
Precisely. Then you have functions, which is the why. Why does the agent need this memory? Is it for facts, for learning new skills, or just holding stuff in its head for a moment?
And then the big one, dynamics. This is how the agent actively manages its own knowledge. This cycle of formation, evolution, and retrieval. This isn't passive anymore.
And that's the whole point. This framework is so crucial because it shows us the gap between what we have now and what we need for those really complex, long-horizon tasks.
Yeah, we're not just talking about chatbots. We're talking about agents that can solve problems in benchmarks like GAI or autonomously write and fix code in something like SWE Bench.
For that, you need a persistent, self-managed state.
Okay.
This paper is basically the roadmap for building that.
Okay, let's unpack that. The authors argue the old taxonomies just weren't cutting it. So why did we need this whole reboot right now?
Well, simply put, the innovation in just the last, say, 18 months has been too fast. The old models just couldn't keep up.
So the theory was lagging way behind the practice.
Way behind. The previous ways of classifying memory were really designed for, conversational bots or basic RAG. They didn't have a box for these new complex ideas, like agents that distill their own reusable tools from experience.
It sounds like the moment agents started actually interacting with an environment, using tools, writing code, navigating, the definition of memory had to get a lot bigger than just, remembering the last thing a user said.
Precisely. The core concept, the thing you have to accept, is that an LLM agent needs persistent state. A standard LLM call is stateless. It's a one-and-done transaction.
But an agent has to carry its history with it.
It has to. It maintains this internal state, its knowledge, its history, that informs every future decision, sometimes across days or weeks. Its whole policy is conditioned on this accumulated memory.
And that policy is about more than just generating text, right? The actions are really diverse.
Oh, absolutely. The agent's policy is governing this huge action space. It might be invoking a tool like a code interpreter. It might be doing explicit planning, like breaking a task into sub-steps. All of those actions create artifacts code, reasoning traces, API outputs that have to be fed back into the memory system.
Which brings us to the engine of all this, dynamics. That FER lifecycle. Let's walk through it, not just as definitions, but as operators.
Right. So if the agent is really autonomous, it can't just passively log everything. That would be completely inefficient. So that's where formation, the F, comes in. It's like a selective attention mechanism.
Okay.
It takes all that raw stuff tool outputs, traces, and it filters and transforms it into memory candidates. It pulls out just the useful bits.
So F is like the bouncer at the door, only letting the important information in.
That's a great way to put it. Then right after, you have evolution, E. This is the consolidation phase. It takes those new candidates and integrates them into the existing long-term memory. It gets rid of redundancies. It resolves conflicts.
So if the new information contradicts something old, E is what figures that out.
Exactly. It might even restructure the whole knowledge base. This is what guarantees that state persists across tasks. And then you have retrieval, which is the part we're all pretty familiar with. It pulls out what's needed for the immediate context.
But here's the insight from the paper that I thought was really profound. They argue that short-term and long-term memory aren't separate boxes.
No, they're not. They're emergent phenomena. They emerge from the temporal patterns of how the agent uses F, E, and R.
Whoa, okay, say more about that. You're saying it's not a different place, it's a different speed.
Precisely. If an agent is engaging in that FER cycle constantly, rapidly, for a transient task, that is working memory. If it engages FER infrequently, focusing on deep consolidation and retention, that is long-term memory. The system just needs different speeds for the same core operators.
That reframes everything. Okay, let's use that framework to clear up some of the confusion. This is where it gets really interesting for anyone actually building these systems. First up, agent memory versus what we used to just call LLM memory.
Well, the new definition of agent memory pretty much subsumes those older LLM memory systems.
Mm-hmm.
When you look at something like MemGPT, it was already solving an agentic problem, tracking a long conversation, accumulating experience. It was an early agent architecture.
So where's the line now? What about changes to the transformer itself?
The line is drawn at persistence and deliberateness. If you're talking about managing the transformer's internal machinery, the KV cache or architectural changes like Mamba or RWKV, that's what the paper calls LLM internal memory.
So that's just engine tuning.
It's engine tuning.
Yeah.
It's about making the model run efficiently in a single long context window. It doesn't support that cross-task persistence or those deliberate learned FER operations. Agent memory is about what the system learns. LLM memory is about how fast the engine runs.
That is a super clean separation. Okay, let's tackle the big one. RAG. Retrieval augmented generation. We all use it, but the paper argues true agent memory is fundamentally different.
And it is. Traditional RAG is passive. You have a static external knowledge base. You ask a question, it retrieves something, it answers. The knowledge base doesn't change.
Right.
Agent memory is about proactive evolution. The agent's interactions with the world continuously update and evolve its internal knowledge base.
But what about the new, more advanced RAG systems? I'm thinking of things like HippoRAG, which use knowledge graphs and feel more dynamic. Isn't that blurring the line?
It is blurring, for sure, but the distinction usually comes down to purpose and domain. RAG excels at knowledge-intensive benchmarks, like hotpot QA, where the goal is to reason over a fixed set of documents.
Oh, okay.
Agent memory is built for sustained interaction and environment-driven adaptation. Think about the difference between answering a question about a static document versus debugging a complex software project over 3 days. That requires the memory to evolve with the state of the code.
I see. And then you have agentic RAG, which is the closest cousin.
It is. Agentic RAG is where the LLM actively decides what and when to retrieve. It's almost an FR loop. But crucially, it's still usually operating over an external database someone else created. True agent memory is about the system maintaining its own internal, self-evolving knowledge base.
So it's the difference between consulting a library's encyclopedia versus writing in your own personal diary.
That's the perfect analogy.
Okay, let's shift gears to form. If dynamics is the engine, forms are the components. How is this memory actually architected?
So the paper lays out 3 major forms. The first is the most familiar, token-level memory. This is explicit, it's inspectable, you're storing information as discrete units, usually text. The big advantage is it's transparent. You can see it, you can edit it.
And this is where the paper talks about dimensionality, which I thought was a clever way to frame it. Why would an engineer choose a simple, flat 1D memory?
Well, it's that classic trade-off. Flat memory, or 1D, is just a raw log, a simple text file of experiences. It's super simple, it's easy to scale, and it's great for just broad recall.
But not very organized.
Not at all. The moment you add organization, you move to planar memory, or 2D. You start using trees or single-layer graphs. Now, you can do relational traversal, but your implementation complexity just shot way up.
And at the top, you have hierarchical, or 3D, memory.
Right. Multi-layer structures, like pyramids or nested graphs. This is what lets an agent do vertical abstraction, moving from raw data at the bottom to high-level summaries at the top. For a complex, multi-step problem, that's incredibly powerful, but the overhead to manage that structure is significant.
Okay, the next form is more opaque, parametric memory. This is knowledge encoded directly in the model's weights.
Right, this is the agent literally changing its mind or its brain.
Yeah.
And we can split this into internal and external. Internal is when you bake knowledge into the original model weights, like through fine-tuning.
The access is instant, I imagine.
Instantaneous.
Yeah.
But the update is high cost and very risky. You're messing with the core model, which opens the door to catastrophic forgetting.
Which is why the external approach became so popular. Things like LoRa.
Exactly. External parametric memory stores new knowledge in these smaller auxiliary parameter sets, like adapters or LoRa modules. It's the best of both worlds, really. It's modular, it's flexible, and you can add new knowledge without destabilizing the whole foundation model.
And the last form is latent memory. This is implicit, machine native, carried in things like hidden states. This has to be the most efficient at inference time.
It is, because the information is already right there where the computation is happening. But managing it is tricky. The paper groups the techniques by their origin. You can generate, reuse, or transform these latent states.
Okay, let's start with generate.
Generate means you use an auxiliary model to synthesize a compact representation. Think of gist tokens, where you compress a huge history into just a few special tokens. It's great for compression.
But you risk losing information.
You risk information loss, and you have the overhead of training that separate compressor model.
So if you want perfect fidelity, you'd go with reuse instead.
Right. Reuse is just directly propagating the raw computational states, like the KV cache. You get perfect fidelity, zero information loss, but that cache grows incredibly fast. It becomes a huge memory bottleneck.
So we have this tension between compression and fidelity. I'm guessing transform is the middle ground.
That's exactly it. Transform techniques try to modify or prune existing latent states. You see this in methods like scissorhands, which intelligently drops less important tokens from the cache. It's a balance, but it adds its own layer of complexity.
That's a great overview of the trade-offs. Okay, let's pivot to function. Why does the agent need all this? What's the purpose?
So the paper defines three functional pillars that, sort of mirror human cognition. The first is factual memory. This is your declarative knowledge. It stores explicit facts, user preferences, the state of the world, things like that.
And its goal is just to be consistent and adaptable.
Right. And you can break that down into user factual memory, which is for things like conversational coherence, remembering a user's goals. Then you have environment factual memory, which is about the external world.
Which is critical for multi-agent systems, right? They need a shared source of truth.
Absolutely. Systems like MetaGPT use these shared memory pools so a team of agents can coordinate plans and see the same state of the world. You can't have 5 agents working on a code base if they all have a different memory of what the code looks like.
Makes sense. The second pillar, experiential memory, sounds like learning from doing.
That's what it is. It's procedural knowledge. It lets the agent get better over time without costly retraining. At the lowest level, you have case-based memory. This is just storing raw trajectories of successful or failed attempts. It's like a library of very specific examples.
Then you move up an abstraction from there.
To strategy-based memory. This is where the agent distills a general pattern or workflow. Instead of remembering one specific website login, it learns a general strategy for navigating login pages. It's a cognitive scaffold.
And at the very top is skill-based memory.
This is the agent's toolbox. It's the actual executable capabilities, code snippets it knows how to run, APIs it knows how to call. It's the active part of procedural memory.
And finally, working memory, the scratchpad.
Right, the transient capacity-limited workspace. For a single turn, this is all about managing huge inputs. Techniques like input condensation, where you discard predictable tokens, or observation abstraction, like turning a video stream into a simple text description.
And for multi-turn tasks, it's about not getting lost.
Exactly. It's about maintaining temporal coherence. You see techniques like hierarchical folding, where an agent finishes a subtask, compresses the or open to a summary, and clears that working space for the next step. It's about integrating memory retrieval right into the planning loop, so the agent always knows where it is and where it's been.
So if you were to summarize the big shift this paper documents, what would it be?
I'd say the field is moving beyond memory as a passive database. We're past the days of just retrieving from a static vector store. Agent memory is now defined by its dynamics, the active, self-optimizing FER cycle. It's a core component of intelligence itself.
So looking ahead, where does this go? One area that seems fascinating is this idea of memory generation. Not just retrieving, but creating memory.
Absolutely.
Yeah.
When humans recall something, we don't just pull up a perfect video file. We reconstruct the memory. It's a constructive process, and systems like MemGen are trying to do that, synthesizing knowledge or compact states on the fly instead of having to store every single thing perfectly.
And I guess reinforcement learning is how you teach an agent to manage all of this effectively.
It has to be. You're talking about a complex, sequential decision-making problem. When should I form a memory? What should I consolidate? What should I forget? We're moving from simple heuristics toward fully RL-driven memory managers that learn and act memory policy.
And the ultimate goal of that policy is to maintain a coherent world model.
Yes. The big vision is a kind of dual system architecture.
Yeah.
A fast reactive system 1 for immediate tasks,
Yeah.
and a slow deliberative system 2 that uses this rich memory system for planning and reasoning. That active memory policy is what keeps the system 2 world model up to date and accurate.
So here's the final provocative thought for everyone to chew on. The paper suggests that to solve the ultimate challenge, the stability-plasticity dilemma, learning new things without forgetting old ones, future agents might need something analogous to biological sleep.
It sounds a bit like sci-fi, but it's grounded in real neuroscience. The idea is that the agent needs dedicated offline time, a sleep state, to consolidate all the raw episodic memories from its day into efficient, generalized parametric intuition. It's about active reorganization and, crucially, active forgetting. It suggests that for an AI to become truly intelligent, it might just need some time to dream,